Hello, and welcome to this short presentation on semantic web technologies. My name is Joe Gregory, and I am an engineer working for Perpetual Labs. In this presentation, I'll provide a brief introduction to the semantic web before going on to explain how engineers can use RDF and OWL to leverage those semantic web technologies. I'll talk a bit about the power of reasoning and querying and the importance of establishing viewpoints. First, though, I'd like to point out some useful resources. There are loads of really useful resources available online, and I've reused some of their points in here. Please do visit them for further information. First, let's introduce the idea of the semantic web, and semantics in particular, and explain what that means. Information can be described as data plus context. When information is held by a person or a machine, it becomes knowledge and has meaning. If we have data and a human understanding of the meaning, we can use artificial intelligence to produce machine interpretable knowledge. One way of doing this is via statistical approaches such as machine learning and data mining. Another way of doing this is via a symbolic approach, such as using ontologies and automated reasoning. It is this symbolic approach regarding the formal understanding of symbols that is the focus of this presentation. So why is this use of symbols important to understand? Well, take a look at this image. You may know that the text, "Ceci n'est pas une pipe," translates to "this is not a pipe." And of course that's correct, this is not a pipe, this is a representation of a pipe. More specifically, it is a painting of a pipe. The painting itself symbolises a pipe, but the painting itself is not a pipe. It cannot hold tobacco or be smoked, for example. It is important to distinguish between the symbol and the concept that is represented by the symbol. Here's another example. Take a look at this word, Tesla. So what does that word mean to you? The word itself symbolises something, but what? Well, you may think of the organisation, Tesla Incorporated. You may think of this particular type of electric car, often referred to simply as a Tesla. You may think of the inventor and engineer himself, Nikola Tesla, or you may think of the SI unit for magnetic flux density. The point is, for communication between two parties to work, the syntax is not enough. We need to be absolutely sure that we are using the same symbols to represent the same concepts and that we have a shared understanding of the context. The semantic web aims to resolve some of these difficulties. The original web was essentially a web of documents. These documents, or web pages, contained largely static data formatted using HTML and connected via hyperlinks. Data connected in this way is largely uninterpretable by machines. And that introduces numerous limitations to this approach. Consider an information retrieval task, using the same Tesla example as before. With no understanding of the context, results can be irrelevant and searches are inefficient. Information extraction is often a manual exercise in which blocks of text must be manually scrutinized. The semantic web offers some solutions to these issues. The word semantic refers to meaning in language or logic, and the term semantic web was coined by Sir Tim Berners-Lee in 1999 to refer to the structuring of data on the web in such a way that it can be read and interpreted directly by computers. Essentially, the machine understands the meaning of the data. In systems engineering, we are seeing a similar evolution in terms of the structuring of our data. Other disciplines, biomedical for example, are further ahead in the adoption of these semantic web technologies. The goal then is to adapt them in our domain to enable semantic systems engineering. And there are two key steps to achieving this that I'll talk about today. The Resource Description Framework, or RDF, makes information machine readable, and the Web Ontology Language, or OWL, provides context to this information. So first, what is RDF? RDF makes knowledge machine readable and works by replicating human sentence structure. Information is captured using RDF triples, subject, predicate, object. Complex knowledge graphs can then be constructed by combining these RDF triples. RDF is built using unique resource identifiers, or URIs. URIs are similar to URLs, but refer to resources rather than documents. URIs can refer to concepts, objects, things, relationships, and they become the single source of truth for that resource. In this way, data can be added to the knowledge graph as necessary. This example, a snippet from a knowledge graph of novels, shows that 1984 has the author George Orwell. The subject, predicate, and object all have specific URIs. So, building on this example, if someone has author information for the novel 1984, and someone else has publication information, as the subject in each triple has the same URI, the knowledge is merged into a single knowledge graph. Further knowledge can then be added as necessary, including the genre, other books by the same author, and the genres of those other books. To really leverage the power of semantic web technologies, we want to add context to this information and define some rules. We can do this using the Web Ontology Language, or OWL. An ontology is a formal, explicit specification of a shared conceptualization. It essentially defines the allowable terms and relationships within a knowledge graph. OWL is the standard language for authoring ontologies and builds on RDF. Ontology is needed to define a consistent formal understanding of the terms and relationships within a domain, as demonstrated with the earlier Tesla example. Using the same RDF triple structure, we can define allowable terms and relationships. Examples include a simulation produces results, a function has at least one input and one output, and a verification method is a type of process. So, looking again at an example of knowledge regarding novels, we can say that a novel has an author, it is of a particular genre, it was published in a particular year and by a particular publisher. Extending our ontology further, we can say that an author is a person, and therefore, like all people, an author must have a birth date and a nationality. We might also wish to define explicitly that publication date and birth date are both types of date. We can provide cardinality constraints to define the cardinality of properties. For example, a person must have at least one nationality and exactly one birth date. The ontology can also be known as the terminological box, or T-box. Instances of these types can then be defined in the assertional box, or A-box. So with an ontology defined, we are now capable of performing reasoning. As the instances defined in the A-box inherit all of the properties of their type defined in the T-box, we can now ask the machine to reason with the information to infer new information. An example is as follows. Our simple novel ontology has been defined, and we want to add information regarding the novel 1984, which is an instance of the type novel. We can populate our knowledge graph with other information we have. It was published in 1949 by Secker and Warburg. It was authored by George Orwell, who has a birth date of 1903 and is of English nationality. If, however, I mistakenly add the year of George Orwell's death as another birth date, we can immediately see that the rules of the ontology have been broken. No person can have two birth dates, and this inconsistency will be flagged. Beyond the machine's capabilities of inference and reasoning, we may want to produce our own custom queries. We can make queries like, which of George Orwell's novels were published first? Or show me all of the publishers that George Orwell used. This information can then be derived from the knowledge graph. This is much more efficient than manual data extraction in the sense that we discussed earlier when looking at Tesla. In fact, the semantic web is already capable of this kind of relevant information extraction using this kind of query. Furthermore, the querying of graph databases is significantly more efficient in terms of time than querying of relational databases. An example of what this kind of query might look like is provided here. It is written using Sparkle, a widely used query language, and it asks an example geography ontology, what are all of the country capitals in Africa? So finally, a brief word on viewpoints and why we need them. Ontologies and knowledge graphs can get pretty complex pretty quickly. Most people working on a particular project or within a particular domain will not be interested in the entire domain ontology, but rather a particular aspect of it. Viewpoints allow us to focus on particular areas of the knowledge graph. For example, a viewpoint might address a particular stakeholder concern, or a particular process, or a particular information artifact. We'll take a look at a simplified design and manufacturing ontology as an example. From this diagram, you can see that this relatively simple, incomplete ontology is already difficult to understand and communicate. It contains many types of class and property. Examples include OEM is a subclass of organization, requirement spec comprises requirements, and results verify product design. By presenting this ontology in multiple carefully selected viewpoints, it becomes easier to comprehend. We may choose to include a product viewpoint, which is interested in aspects of the product itself. This viewpoint captures what the product design itself comprises and the processes required to yield the product design and the physical product. This organization viewpoint shows all types of organization defined in the ontology, the processes that they are responsible for, and the outputs of those processes. The taxonomy viewpoint contains only the subclass of relationships, which captures the hierarchy of the allowable terms. Different organizations may wish to present the same information in different ways. In this example, Autodesk are a Tier 1 organization responsible for the design process of a heat exchanger. They may wish to view this list of product components alphabetically. In the same scenario, LPW are the Tier 2 organization responsible for the heat exchanger manufacturing process, and they may wish to view the list of product components in the order that they are manufactured. So, to sum up, critically, we communicate via symbols and representations, so it is crucial to understand the context. The semantic web operates at the data level rather than the document level and makes the information machine interpretable. We can adopt these technologies in engineering. RDF triple structures make knowledge machine readable, and OWL allows engineers to build an ontology of allowable terms and relationships, thus providing context. We can get the computer to use these relationships and rules to reason with the data and infer new knowledge, and we can build custom queries to push this capability further. A complex ontology can be presented in multiple viewpoints. Roughly speaking, these viewpoints correspond to a particular set of stakeholder concerns. Finally, please do refer to the list of resources provided for further information. Thank you for listening.